Thanks for the introduction. Yeah, so this is joint work with John Wright, who's currently a postdoc at Caltech and is going to start a professorship at UT Austin next year. Actually, just before I start, I want to get a feel for the audience. So just by show of hands, how many of you would define yourselves as quantum people? Okay, this is a very quantum audience. Okay, that's good. Okay, so let's just get started. So this talk is about interactive proofs in the quantum setting. So I'm just going to start with some basic definitions that if you went to Alex's talk yesterday, you've already seen, but just to refresh our memory here. So like in interactive proof systems, you imagine you have some verifier that's a polynomial time machine, but it gets to interact with a prover that's all powerful, can do anything it wants, but you can't trust it. And so the prover is trying to prove to you that the answer to some, say, decision problem is yes, and you, the verifier, to decide whether to believe the prover. So we say that a proof system has completeness if the answer really is yes, then there's some proof that the prover can exhibit to you that convinces you that it's yes. And I've written probability 1 here because in this talk that's good enough, but you could have any large probability. And then this property called soundness is that if the answer is no, then there's no like false proof that the prover could send to you that would make you accept. So with high probability. So here it's just I picked a half. You could pick whatever constant you want. So that's the basic setup for interactive proofs. And so you can already think of NP as sort of like a non-interactive proof, right? Like the prover just writes down a proof that's polynomial size and sends it to the verifier, and the verifier checks it deterministically. But we sort of know that if you allow for randomness in interaction, so the verifier can generate random challenges for the prover, then this already makes the class a lot more powerful. So the corresponding complexity class is called IP, and it's known to be equal to P space. So anything you can do in polynomial space, you can also prove to a polytime verifier. So that's the basic model. So what's one way you could augment this is you could imagine having more than one prover. Okay, and for this audience, I guess many people have seen non-local games, so this type of picture should be quite familiar. But just to review, what we have here is we have the verifier, and this diagram here is sort of a 2-prover, 1-round interactive proof protocol. So what's going on here is the verifier first flips some random coins and picks a pair of questions, X and Y, to send to the 2 provers. It sends Alice the first question X and Bob the second question Y. And then the provers come up with answers, A and B. They send them back to the verifier, and then the verifier decides whether to accept or reject the prover's answers. So, and in general, you could allow for more provers and more rounds of interaction, but actually in this talk, we'll restrict to 2 provers in 1 round. So the complexity of this class is also fairly well understood. So we know that it's actually a lot more powerful than IP, so it's equal to NEXP, non-deterministic exponential time. So just for concreteness, that's like saying that if you want, these multi-prover proof systems can prove to a polytime verifier that an exponentially large graph is 3-colorable. Which is kind of neat because, like, you naively think that such a protocol would involve, I don't know, querying for the color of like 1 or 2 of the vertices, and that clearly cannot work because the graph is exponentially big. But there's like these clever encodings that you can use that let you actually do this. So where did this extra power come from? Like, why is MIP so much more powerful than IP? Well, it's I guess you could say it's because the provers here are assumed to not communicate. And that gives the verifier a lot of power to detect cheating. Like the verifier can send 2 sort of different questions to the 2 provers and then do a consistency check on their answers. And it makes it a lot harder for the provers to deceive the verifier. That's my intuition for why this class is so powerful. And then you might ask, in the physical world, how do you prevent the provers from communicating? And the answer is, well, one answer is you could use relativity, right? You could separate the provers and then run the protocol quickly enough so that the speed of light barrier prevents any messages from being sent between them. Okay, now I have no need to motivate for you that we should, now that we're talking about physics, we should also consider what happens to this model in a world where quantum mechanics is true in our world. So what about if there's quantum entanglement between the provers? So as we know that quantum entanglement does not allow you to send messages faster than light, so it doesn't change this property that the provers are non-communicating, but it can let you share correlations that you wouldn't have classically. So sort of, Bell already discovered this, like the Bell test, you can view it as one of these MIP protocols in a sense. It's not a protocol for a computational problem, but it's some protocol where entangled provers can succeed with a higher probability than non-entangled provers. So, right, and then you could just define the associated complexity class and say, okay, what if I consider MIP, but I allow the provers to share an arbitrary entangled state? Then what's the power of this class? By the way, I just want to mention that, okay, you might wonder why is it an arbitrary entangled state? Well, I guess this is just like sort of the standard, the most natural definition. When you think of, in general, these interactive proof classes, the prover is always assumed to be all-powerful. And so here we're saying the provers have like not only whatever computational resource they want, but also any physical resource, just subject to this non-communication limit. So that in particular allows them to have any entangled state. So that's, I guess, why that motivates that definition. Okay, so now we'll get into the complexity theory of this class a little bit. So what is the power of MIP star? Well, the thing is that when you have to be careful with these interactive proof classes, because whenever you give more power to the provers, that doesn't necessarily make the class more powerful, right? Because remember, there are two properties you need to have, completeness and soundness. And so sometimes when you give the provers more power, that makes it easier for cheating provers to come up with false proofs and deceive the verifier. And that's indeed something that can happen with MIP star. So this classic work of Cleve et al., they showed that there's a particular type of MIP proof system called a XOR MIP, where I guess the verifier only computes the XOR of the bits returned by the provers. And that proof system is already classically powerful enough to prove NEXP. But the same proof system with entanglement is no longer sound. So it's actually contained in exponential time. And so if you know about like two-player XOR games, this is sort of the reason why this happens is because there's this efficient characterization for two-player XOR games when there's quantum entanglement, whereas this does not really exist for classical XOR games. So in principle, adding entanglement could have actually made MIP star less powerful. It could have been the case that even if you remove the XOR symbols here, that MIP star is contained in X, but MIP is equal to NX. Okay, so a priori that was possible, but turns out not to be true. So there's this work by Ito and Vidick in 2012 who showed that a different MIP star protocol for NX can be made sound against entanglement. And so here, just to sort of stress what they're doing here is they're taking a classical protocol for NX, and in the completeness case, like the case where the provers are behaving honestly, they don't need to use any entanglement. It's a fully classical protocol. It's just in the soundness case where you want to guard against dishonest provers, they show that entanglement cannot help the dishonest provers to deceive you. Okay, so that's what we know in terms of lower bounds on MIP star. Oh, sorry. Any type of entanglement. The only technical thing I would say is that we do assume that it's some finite dimensional entangled state. But yeah, that's it. That's right, yeah. I think you can show by some convexity argument that a pure state is always optimal. Like there's no need for them to use mixed states. But yeah, they could have no need for it to be like EPR pairs. It could be any entangled state. Yeah. That's right. Sorry, are there any other questions? Yeah. Yeah, that's right. And there are like techniques to amplify these things, like parallel repetition and so on, so that don't increase the number of rounds. So the 1/2 is kind of arbitrary. Okay, so that was the lower bound side. What about upper bounds? Well, we get exactly this question. They're just asked that in order to prove an upper bound on this class, you sort of have to think about how could the entanglement be used, right? How could it possibly help you? And the thing that we don't know is that it's certainly possible that these provers could do something with a very high dimensional, very complicated entangled state that they couldn't do with anything smaller. Like there's no upper bound on the amount of entanglement they need to use. And actually, computationally, the best upper bound on this class that we know to date is the class RE, which is recursively enumerable languages. So what this class, if like me, you've forgotten what it means, it's the class for which the halting problem is the complete problem. So it's like sort of like if the answer is yes, then there's a Turing machine that halts and tells you it's yes, but if it's no, then the Turing machine may never halt. And so why does this bound hold? Well, the Turing machine that you construct is one that just searches over all possible entangled strategies that the provers could use by brute force. It's sort of like, oh, I'm going to first check all the classical strategies, and I'll check all the strategies that use 1 bit of entanglement, all the ones that use 2 qubits of entanglement. Or maybe I should talk about dimension, like all the strategies with like dimension 3, dimension 4, and so on. And then, you know, in sort of the case where there is a good strategy, eventually this process will halt, and your Turing machine will say, ah, there is a good strategy, so you're in the yes case. But if there's no good strategy, then you can't, you know, your Turing machine may never halt because it'll just keep on looking forever. So that's why you have this upper bound of RE. So in particular, that means that, you know, MIP star might contain computational problems that are undecidable. It's something we don't know how to rule out yet. Okay, so that's sort of the landscape of computational results, I guess, known prior to this work. And okay, so if you want to go beyond the lower bound here of NEXP, you sort of need to use the entanglement somehow, even in the completeness case. So like even in the honest case. Sorry. That's kind of related. So the reason, okay, so the reason they don't consider infinite dimension, it's sort of related to this question of whether you define entanglement by the tensor product or by having like commuting algebras of observables. So in the tensor product model, it turns out that any infinite dimensional tensor product state can be approximated arbitrarily well by finite dimensional tensor product states. So then it's really equivalent to do this because sort of you're taking a limit anyway, because you're always talking about like the limit of the best strategy, and so it doesn't matter whether you say it's finite or infinite. In the commuting model, then it absolutely could matter, and I guess the distinction between the two is very poorly understood. Okay, so I guess the point I want to make here is that, okay, so you want to go beyond NX, so you have to somehow use the entanglement in some way that to do something that you could not do classically. And what's one such thing? Well, many of you will probably have heard of this phenomenon, but it turns out, you know, this dates all the way back to like Bell's game. I guess Bell's game has this property that many of these sort of two-prover protocols that involve entanglement have this nice property that there's, you know, when there's a quantum strategy that does better than any classical strategy, that quantum strategy is sort of very strongly unique. So not only is it's like unique up to isometry, but also it's like robustly unique in the sense that if you succeed in this protocol with a probability that's even close to the optimal quantum winning probability, then the state and measurements you use have to be close to this optimal state and measurements in the appropriate distance metric. So that's something that's called self-testing, and you can think about it as like, you know, the provers are proving to you not a computational fact, but a physical fact. Like they're proving to you that their systems are in this particular quantum state. And that's something that doesn't even make sense to talk about classically, right? Because like all classical states, I guess, kind of equivalent to each other. So it's a uniquely quantum power, and so we'd have to somehow, it seems like natural that we'd want to exploit this power. So I just want to summarize a bit of like what self-tests can do. This is a very not at all comprehensive summary, but okay, so the classic results here, you know, things like the CHSH game, I guess that they were analyzed by later people like Cyrilson and Summers and Berner and many others. So they're able to design these tests that can certify that you have a single EPR pair of entanglement if you succeed in these protocols with high probability. And then there are sort of more modern tests that can actually test many qubits of entanglement. So one thing that we can do now is you can test that the two provers share n copies of the EPR state with an amount of communication that's efficient in n, so only logarithmic in n. So that's a work that by Thomas Vidick and myself. So that's somehow that I guess we're going to use that in our protocol. There's also been some complexity theoretic hints that entanglement can help. And so one idea that people have had is that maybe you could use self-testing to design an MIP star protocol for some problem by, instead of self-testing just copies of the EPR state, you could self-test some state that's computationally hard to produce. So there's some work, I guess we had this work on self-testing history states that lets you at least do QMA. And I guess the interesting thing here was that you could do QMA in MIP star, and okay, that's not very interesting because MIP star at least contains NX, which is way bigger than QMA. But you can actually do it with log size messages. So this is it's like kind of like a quantum version of like this of the classical fact that you can do NP in MIP star with MIP with log size messages. Okay, so that's one hint that MIP star could be more powerful. Another hint is there is this pair of works by Zhengfeng Ji and some other authors that showed that you could get actually much larger classes in MIP star if you allow this completeness soundness gap, so the difference between the completeness probability and the soundness probability, to get very small. So they designed these protocols where, say in the yes case, you can convince the verifier with probability 1, but in the no case, the verifier will still be falsely convinced with probability that's like 1 minus 1 over an exponential, or 1 minus 1 over a doubly exponential. But the neat thing is that if you allow for this tiny probability gap, then you can solve much more computationally difficult problems. And all these results sort of use this idea of you'd design a self-test for not the EPR state, but the history state of some Hamiltonian. So or I guess the history state of some computation, which you check with a Hamiltonian. And that had some, there's some like technical issues associated with this. Like you'd always need to have more than 2 provers, and sort of the fact that circuit to Hamiltonian constructions are very non-robust meant that these protocols were also kind of non-robust. Like in some sense, that's responsible for this tiny completeness soundness gap here. Okay, so that's I guess the prior work on lower bounds. And then, okay, so let me just get to our result. So the result was already in the title, so but I'll restate it here. So the thing we show in this work is that actually MIP star contains, even with a constant completeness soundness gap, it contains the class NEXP. So this is like NX, but one more exponential. So it's non-deterministic time of 2 to the 2 to the poly n. And the protocol we construct has a bunch of nice properties. So it's just 2 provers, 1 round. In the yes case, it has perfect completeness, so the verifier will accept in probability 1. And in the no case, the soundness is a half, and you can amplify it to whatever constant you want for the parallel repetition. So just to make this like concrete again, like the complete problem for NEXP is 3 coloring for graphs that are doubly exponentially large. And by the way, in case you're wondering, how do you even specify the input to this problem if the graph is doubly exponentially large? Well, there's like actually there's a standard trick for doing this. Like even with NX, you have to come across this issue, and you have to succinctly encode the graph. So this is a super succinctly encoded graph. And we call this like succinct 3 coloring. But okay, so there's this graph that's doubly exponentially big, and you can certify that it's 3 colorable. And this is kind of I guess wild in the sense that the messages here that the prover and the verifier are exchanging are all polynomially many bits, and that's not even enough bits to specify one vertex in the graph, right? Because the graph is so big. It's like you can't even do this naive thing of like querying for a pair of vertices and asking for their color. Like this is impossible in this setting. Okay, so what are some corollaries of this? Well, one corollary is that we show that MIP star is definitely more powerful than MIP. So entanglement definitely makes this class more powerful. And why do I say unconditionally? Well, it's because of the non-deterministic time hierarchy theorem. So that tells you that NEXP is just known to be distinct from NXP. So that's one corollary. Another thing is this point that I was making earlier that in order to achieve this, you need to use the entanglement even in the completeness case or the honest case, and that's the case for us. So in our protocol, even the honest provers need to share an exponential number of entangled qubits. So this is different from the Ito and Vidick protocol where they didn't need any. And then finally, this is just a technical point. If you care about history states, this protocol does not use any history states. So I think that makes it a little bit simpler to understand. And you also avoid these technical issues I mentioned on the previous slide with robustness. Okay, but you can ignore that point if you're not familiar with these history states. So, yeah.
That's what makes the move from exponential to double exponential. So you allow it to be exponentially large.
That's right.
Can you aspect it? So if you let it doubly exponential entangled state or doubly exponential qubits, you can raise another exponential with this.
That's a very good question. Say we're working on it. I'll have a slide about that at the end. Yeah, it's definitely seems like the natural thing to do next. So I guess after I explain the proof, I can tell you sort of why it's not immediately clear how to do that. Like there are some technical problems to solve. But yeah, that's the next thing to do. Oh yeah, I should also say maybe it's one point I could make is that since this state, you could imagine like considering what's the power of MIP star if you just like impose a restriction on how big the entangled state is. And so if you say I'm going to require that the entangled state be at most exponentially many entangled qubits, then it's not hard to see that there's an upper bound of NEXP, just because sort of the algorithm would be to guess a classical description of the exponentially big state, and you can write that down in 2 to the 2 to the n classical bits, and then like compute whether that classical description is a description of a good strategy.
What would be the implication, you touched that later, of having not a particular maximum entangled state, which is the case, but some noisy case? Would that affect the probability of the completeness?
Oh yeah. Definitely. So, well, if you tried to use our protocol, but you fed in a noisy state instead, then you'd just fail. So like your completeness would like drop down to close to 0.
No matter how small.
No matter how, as long as it's like for any constant noise per qubit, then you'd be doomed. Yeah, because like the measurements that the provers are supposed to do are like they're like very non-local measurements. They have to like measure all their EPR pairs and do some computations on the outcomes that are not robust to the things they get out. So yeah. Yeah. It's not like noise tolerant, maybe. Yeah, that's right, yeah. Yeah, I think that's actually an interesting open question because I don't know if you're familiar, there's this work by Penghui Yao that's like sort of studying the noise robust version of MIP star where you just require the states to be noisy copies of some qubit state. And there you can sort of show some upper bounds. But I think it's definitely conceivable that the noise robust version is just like very different from the zero noise version. Because there's like things you can do in zero noise and you can't do otherwise. Okay, well, I should say, so this is all I have to say about the result as such. So if there's any more questions about what the result means or implications, now's a good time to ask. Okay, so maybe I'll move on to, okay, so the rest of the talk I'm going to kind of try to sketch how we prove this, and then maybe some future work. So, okay, so how do we prove this? Well, the idea is essentially a kind of a compression type argument. We want to take some protocol and some very large protocol and shrink it down. So the way you might come to think of this is just, how would I come up with any sort of multiprover protocol for this class NEXP? Like, what's the most naive thing I could do? Well, one thing I could do is just start with the classical MIP equals NX protocol and scale it up by an exponential. So that's the first step in our construction, is we just do this. And so what you have at this point, you have a protocol for NEXP, where the messages, the questions that are sent by the verifier to the provers are exponentially long, and the answers that the provers send back to the verifier are also exponentially long, right? Okay, both of these things are unacceptable for us. So then what we're going to do is just sort of transform this protocol until both those things are polynomials. So we do it in 2 steps. In the first step, we try to shrink the questions. So we map this to a new protocol where the questions are only polynomially long, but the answers are still exponential. They actually get a little bit bigger when you do this. And notice that there was no star over here, but there is a star over here, and that's because this protocol didn't need any entanglement. I guess it's sounding as entanglement, but you don't need to use it. Whereas once you do this transformation, you absolutely must use the entanglement. Like the entanglement is needed for even the honest provers. So this is, I guess, I feel like the most unique step of our construction. And then the second step is, you probably can guess, answer reduction. So you have to somehow make the answers short now. And indeed, you can do this. So you make the answers polynomially long, and the questions are still polynomial. Like they blow up by a little bit, but they're still bounded by a polynomial. So I hope it's clear that if you could do both of these things, then you're done, right? Because the protocol you get out at the end has the right parameters. So this answer reduction is sort of, actually, if you're familiar with the classical literature on PCPs, it's kind of an instance of PCP compositions. This is a trick that has a long history, and it's sort of a generic thing that you could do. So I'll talk a little bit about that at the end, but I'm going to try to focus mostly on the question reduction, because I think that's like the sort of the new thing here. Okay, so what are we trying to do in question reduction? Well, let's write down the protocol we start out with. So we started out with this exponentially big protocol, and how it works is that, remember, the verifier has to first sample a pair of questions to send to the 2 provers, right? And they're sampled from some distribution. Let's just call it D. So how are we going to reduce these questions? Well, what we're going to do is, instead of having the verifier do this sampling, we're just going to ask the provers to do it for us, using their entanglement. So the new protocol will just look something like this. The verifier will just say, hey, provers, I hope you have the appropriate entangled state that I instructed you to prepare. I'm now going to ask you to, if you're Alice, I want you to do one particular measurement to your half of the state, and if you're Bob, I want you to do some other measurement, and then your measurement outcomes will be strings x and y that are distributed according to this distribution that I wanted you to sample from. And then, like, once you do this, then Alice will just take her measurement outcome and execute the protocol as she would have done so here. And Bob will take his measurement outcome and do the same, and then they'll return their answers and also the question that they obtained from their measurements. And then the verifier will check. So here the answers are still exponentially big, and you can see they're a bit bigger because I have to include the questions I sampled from the entanglement. But now the questions are very small. They're just instructions to measure your entangled state. So, okay, so this would be very nice if it was possible, right? But there are a bunch of potential issues with this idea. So the main issue is, like, how do you know that they're actually doing this, right? Like, you told the provers to measure their entangled state and obtain these things, but maybe they don't even have an entangled state, right? Maybe they just have written down somewhere their preferred pair x, y, and they know the correct answer to this pair of questions, and they can always fool you by returning that x and that y. So, like, for instance, if you think about this in the classical case, like if there's some shared randomness that they share, you can sort of never certify that they use shared randomness. Like, they can always pick one particular particular random seed, and then you will never be the wiser in one of these like single round protocols. So so you have to somehow force them to do the appropriate measurements on the appropriate state, and you need to design the state and measurement so that the distribution of the outcomes is actually the correct distribution. So that's challenge number one. That seems kind of within our reach though, because as we mentioned, we have this power of self-testing that lets us force the provers to apply some particular quantum strategy. The second problem is, I think, a little bit more subtle, and it's this. So even if they do apply the correct measurements to the correct state, you have to sort of prevent them from doing any additional measurements. So if in this protocol, say Alice does her measurement, she learns X. What if she did some other measurement that revealed what Y is, or some additional information about Y? Then this would be bad, because then the protocol would no longer be sound, right? Remember, the whole soundness that we started out with rests on this assumption that Alice did not know what Bob's question is, right? Because they cannot communicate. And so if Alice is able to learn what Bob's question is, that means she can cheat. So we have to somehow certify that Alice has no information about Y beyond just like what she knows by learning X. And likewise, Bob should have no information about X beyond what he learns from learning Y. Yeah. That's right. Yeah. Okay. So the protocols I've drawn here, yeah, you're right. You don't really need to send any measurements because the provers know what they are. But like in practice, you're going to have to send measurements. There'll be additional messages that are like, do this query from this particular game, which is a self-test, and certify that you have this many PR pairs. And then also we'll want to sort of permute like which player plays which roles. Like the players may not know whether they're Alice or Bob until the game starts, and you might want to play two Alices against each other, and so on. Okay, so these are the two issues we need to solve with this question sampling procedure. So I'm going to explain to you how to do that. But first, let me just tell you what we can do with self-tests. So this is like an abstraction for what the self-tests give you. So using the self-test, what you can command the provers to do is you can always force them to have a strategy of the following form. So you can force them to have a bunch of blocks, an entangled state that's like a bunch of blocks or registers, and each register has an exponential number of EPR pairs in it. So that's what like each of these green swigglies is representing, and then you can command them to measure each register in either the Pauli X basis or the Pauli Z basis. So you can say, measure all of your qubits in the X basis and get out a string that's exponentially many bits, or measure them all in the Z basis and get exponentially many bits, or you can tell them ignore this block, don't measure it. So that's like the basic power you have, and it turns out that you can do this with like questions that are quite small, and they're polynomial in n, whereas the number of qubits here was exponential in n. So I'm going to have to show how to use that power to do this question sampling task. Okay, and then I have to tell you what's the actual distribution over questions that I need to sample from. So when we design our protocol, it seems like the question distribution matters a lot. Like we spent a while trying to formulate it in the right way to make this work out. So it's, I think, a great open question of whether you can do this in general. Like, can you delegate sampling from an arbitrary distribution to provers using self-testing? And we don't know how to do that. We do know how to do it for this particular distribution. So let me tell you what it is. It's this distribution called the plane point distribution, and it comes out of one of the parts of this MIP equals NX protocol called the low degree test. And what it is just the pair of questions x, y is as follows. So the question that Alice gets is a random affine plane in some space over a finite field, f2 to the m. So what is a random affine plane specified by? Well, there's two vectors that span the plane, so it's like the two slope vectors, and it's an affine plane, so it can be shifted from the origin by some intercept. So So there's like an intercept vector and 2 slope vectors. So that's what Alice is supposed to get. And what Bob is supposed to get is a random point on this plane. It's just some point on Alice's plane, otherwise it's totally random. So, okay, so I hope the distribution is clear. So we need to force Alice and Bob to sample from this distribution. So here's the first attempt we could make for doing this. We'll tell the provers to share 3 registers of EPR pairs, right? So they get like 3 sets of random bits when they measure this. And the reason we're gonna do that is that, remember, Alice's plane was specified by 3 vectors, right? And so we're just gonna interpret each register as giving one of these 3 vectors. So we'll just say, Alice, I want you to do a z-basis measurement on your 3 registers of EPR pairs. You'll get out 3 strings of bits, interpret them as 3 vectors, and that's your plane. Okay, and it's easy to see that this gives you a uniformly random plane because these z-basis measurements give you uniformly random bits. So I'm going to tell you what Bob does now. Yeah, so far Bob has not done anything yet. Now, okay, you want Bob to get a point on the plane. So what you could do is say, Bob, you should just measure the first of these registers in the z-basis again. So because it's the same basis on both sides, the outcome that Bob will get is identical to the outcome that Alice got. And that was the intercept of her plane. So Bob is going to take this thing, and now this thing is going to be always equal to the intercept of her plane, of Alice's plane, and he's going to just set that to be his random point. So, and then we're going to tell him to ignore the other 2 registers here. Oh. Oh, that for this attempt, that's fine. Yeah, it could be a completely mixed state. I mean, the entanglement is just like, I guess, certifying that there actually is a mixed state there, right? Because otherwise, it could have been, just a pure state, and you wouldn't have known. But, yeah. Good question. So, okay, as of now, no, and that'll be a problem. So I'll tell you how to force them to erase information in a slide or 2. Okay, but first, let me just tell you. Okay, maybe you guys have noticed that this scheme actually does not work at all. The first issue here is so why would we think that it works? So Alice does indeed get a random plane, and that's good. Bob gets a uniformly random point in the whole space, and his point is always on Alice's plane. But and sort of, if I ignored, there are many different triples of vectors here that can give me the same plane. And so if I just consider the plane, now Bob's point is uniformly random on the plane. But the problem is that Bob's point is sort of very correlated with this description of the plane, right? It's always equal to the intercept. And so that means that Alice can always know which point Bob has, right? Alice knows that Bob is always going to get the intercept. So she completely has learned Bob's question here. So we have no soundness. And then the second point is what Carl was just asking about, is that we just told Bob not to measure these registers, but we don't know how to force him not to measure them, right? So he could just go ahead and measure them without telling us, and then he would have learned the entirety of Alice's question. Okay, so that doesn't work. So we have to somehow hide information. So I'm going to first tell you how to hide the information from Bob. So we'll just keep this part the same. On the first register, we do the same thing. And okay, let's just think back to I guess the Heisenberg uncertainty principle, or non-commuting measurements. So if I measure one thing, if I measure one observable, I erase the information about every non-compatible observable. And so the way we could use that is we could hide these other 2 registers by just asking to measure in a different basis from the one that Alice measures in. So remember, before we had here, we didn't tell Bob what to do, but now we're going to tell him you must measure this part of the state in the x basis. And when he does that, the outcomes that he gets out will be totally uncorrelated with the outcomes that Alice received here. So that prevents him. So if he does the x measurement correctly, then he cannot do the Z measurement, right? Because they're sort of maximally incompatible, and that means that he's prevented from learning these two outcomes. And then, okay, I haven't shown you this in the slide. You can just like assume that the self-test gives you the power to do this, but okay, in reality, how would you force him to do the X? Well, you'd have to, some fraction of the time, ask Alice to also do an X measurement and cross-check them and make sure they get the same answer. But you can sort of imagine there's like a compiler underneath that's generating all these cross-checks. Like you can assume that all the things I said on the self-testing slide are given to you for free, and the compiler inserts them in for you. So you need access to the registers because you have to certify that the registers are present and in the EPR state. And to do that, you need Bob to do measurements on them. So that's why he needs access. Okay, so that sort of takes care of all the data hiding we need to do for Bob. Like he doesn't know what Alice's question is, and so he just gets what looks like a uniformly random point to him, and that's what we want. But Alice is still learning what Bob's point is, right? So we have to now deal with the first register. So we're going to do that with basically the same idea. It's just a little bit more complicated here. And so the way it's going to work is that, remember, what we want is we want Alice to learn this plane that's like spanned by u, v1, and v2, but not the actual location of the intercept on the plane. So it's sort of, she has to learn the u like up to a random linear combination of v1 and v2. And the way we're going to do that is instead of asking her to do a complete x basis measurement, that would just totally erase the information in u. We'll ask her to do a partial x basis measurement, which only erases the component we don't want her to learn. And if you do the calculation, it's actually very simple. What she should do, she just measure sort of the x observable that's like a tensor product of x's wherever there's a 1 in the vector for v1 or v2. So if you do the calculation, the eigenstates of these things look like uniform superpositions over something shifted by multiples of v1 with maybe some phase. And so if she does this measurement, she'll smear out the v1 component of the intercept u. So that's exactly what she does. So we tell her, first measure this partial x information, and then you can do a z basis measurement on whatever you have left. And then if she does this, what she'll get out is some outcome u prime that's equal to u up to some random multiple of these slope vectors. So that means that u prime will be a random point on the plane, but it won't be correlated with u beyond that. So okay, so that's really the entire scheme for sampling the questions. And I guess there's one thing you might ask is, okay, this partial x and then z thing was not one of the powers that I specified in the self-testing slide. So how do you make sure that they do it? Well, you have to design a couple more tests for it. It'll be something like, well, I'll ask Alice to do this, and I'll ask Bob to do maybe a complete x measurement, and then just check that the x part of Alice's outcome matches Bob's outcome. So sort of once you have the ability to do these complete x or z basis measurements, you get the ability to do these partial measurements also sort of for free. Okay, so that's the entirety of question reduction, and I guess now that you've seen this, you can sort of see why it depends on this this point versus plane distribution here, right? Because it's like sort of very important that the information that you wanted to erase was like nicely expressible by a Pauli x observable. Like if it was some arbitrary distribution, we don't know how to do this trick here. Okay, so that's question reduction. Now I'll just say a few words about answer reduction. So the thing that comes out of answer reduction is, okay, remember the questions became small, now we want to make the answers smaller. And so what we're going to do is the following. So we shrank the questions, and now the players have sampled their own big questions. They have their own big answers. Now we don't want to directly check these big questions and answers because they're too big to send back to the verifier. So we're going to ask the players to sort of use the power of interactive proofs to prove to us that they have come with the right answers, like sort of recursively using an interactive proof. And so we're using a variant of these interactive proofs called a probabilistically checkable proof, and we'll just ask each Alice to say, instead of coming up with instead of sending her answer, she'll just come up with like a probabilistically checkable proof that her answer was the correct answer, and then we'll read a small amount of this probabilistically checkable proof, and by the way these things work, we can be confident that she has the correct answer. So this is a technique called PCP composition, because you're sort of composing this outer protocol with this inner protocol for checking the answers in the outer protocol. Okay, so now what I wrote here doesn't quite work for the following reason. It's that really what we want to check is not that Alice has the right answer, because that doesn't really make sense, right? Alice's answer, you can only check whether it's right if you also know Bob's answer, right? There's a correct pair of answers. And so we have to do a little trick called oracularization. And the way it works is sort of you need to check that both of the answers are correct. So some fraction of the time, you need to have one of the provers actually produce both answers so that they can prove to you that both answers are correct. And there's a standard way of doing this. You can take any protocol and modify it so that one of the provers is what's called an oracle prover, and it basically knows everything that's going on in the protocol. So it knows like both Alice's question and Bob's question, it can compute Alice's answer and Bob's answer. It knows everything. And then the other prover will behave as either Alice or Bob. So it's known that this transformation doesn't affect soundness. So if your original protocol was sound against cheating provers, it's still sound even if you have this one oracle prover who knows everything that's going on, which is kind of surprising maybe, because you'd think the oracle prover could because it knows both the questions, it could do some weird thing that it would not be allowed to do otherwise. But this works because the other prover that's not the oracle doesn't know what's going on. It only has one prover's question. And so the oracle prover is forced to be consistent with this ignorant prover. So that's oracularization. That's a standard trick. The new thing that's an issue for us is sort of completeness. Like, how do you actually make this oracularization work when you have shared entanglement? And the reason is that classically, when you think about oracularization, the strategies classically, you can just think of them as like a big lookup table that the provers know for every question they could conceivably be asked what answer they should give. And so then the oracle prover always knows what the other prover would have said if it were given this question. But in the case of entanglement, if I'm, say, Alice, I'm playing the role of the oracle prover, I'm given both my question and Bob's question, and I have to figure out what answer Bob is going to give for his question. And now Bob's answer is going to be computed by measuring his half of an entangled state. And it's not a priori obvious that I can do the same measurement as Alice and obtain the same outcome as Bob does. So that's indeed an issue, and sort of this only works in the case where so the measurements that Alice and Bob would apply are going to commute for the pairs of questions that you ask them. And that's a condition that actually does hold for the protocols that I've shown you. Something you can check, and it's a little bit of a delicate condition. Like, it depends on, like for instance, at some point in our proof, it uses like a magic square game, and there's two equivalent formulations of the magic square game, but only one formulation has this property of being oracularizable. So, yeah. So that's sort of the thing with the commutation. So like here, Alice will get both questions, so she'll be told do the Alice measurement and the Bob measurement to sample the big questions. Bob maybe just gets like, let's say he just gets Y, so he's just told do the Bob measurement. And now the thing here is that the Alice measurement and Bob measurement, you have to design them so that they always commute for any pair that you're going to do cross-checking. Yes, that's right. Okay, so this is actually this is sort of a tricky thing. So these things seem kind of contradictory, and in the end, you can make it work out by for this hiding thing, the way I explained it was that, oh, Alice will measure X and Bob will measure Z or something. But really you introduce like sort of intermediate prover rules. Like you say, well, some fraction of the time, Alice will measure X and Bob is supposed to not do anything. He's supposed to just like measure the identity operator. And some fraction of the time he's supposed to, Alice will measure Z and Bob is not supposed to do anything. And this is sort of equivalent to asking Bob to measure X. But in the honest case, they don't have to do anti-commuting things. Okay, so I guess this is sort of a technical point. So if you don't quite follow what's going on with this commutation thing, that's okay. It's not quite, central to the main storyline, but yeah, it's a barrier we had to overcome. Yeah. That's right. Yeah, his X and A are equal to Alice's X and A. That's right. Yeah. So I just wrote the primes because he could have, in principle. Yeah. Okay, so then, yeah, I guess that concludes what I have to say about answer reductions. This is the main challenge, I think, in doing answer reduction. So, okay, what are some, okay, so now we can step back to like, what are some future directions here? So I think the most interesting future direction is as we discussed, trying to go beyond this result. So, because the upper bound is at RE, there's like no reason to believe that this is at all tight. Like why should we stop at NEX? Maybe it's the lower bound can be improved to be much higher. And this question of what the correct lower bound should be is actually, it has some relevance to things a little bit beyond complexity theory. So to explain that, I have to tell you a little bit about these two kinds of entanglement. So I was saying this a little bit earlier, but so MIP star, it actually is defined based on this one definition, which is the tensor product. And the fact that it's a tensor product is essential to getting this upper bound here of RE, right? Because that's what lets us iterate over all finite dimensional strategies until we find a good enough one. There's another kind of entanglement. Oh yeah, so I have this graph here, and okay, what the graph is supposed to convey is that for this algorithm that iterates over things, it's trying to compute an estimate to the best entangled strategy, and that estimate gets better and better the longer it runs, right? So that's why you have RE. The other kind of entanglement is this thing called the commuting operator model. So in this model, you don't necessarily know that there's a tensor product or that the state is even finite dimensional. So you can't do this sort of iteration. But it turns out that there is an iteration you can do over objects that are sort of dual to strategies, like dual in like the LP duality sense. So there are objects that give you upper bounds on strategies. They're things that say that there's no commuting operator strategy with value better than this. And if you've heard about this, this comes out of the sum of squares hierarchy or the NPA hierarchy for these games. So if you iterate over these objects, what you get is not lower bounds, but actually upper bounds to how good the strategy is. And so, and we know that this iteration will eventually converge to the best commuting operator strategy. So what this means in complexity terms is that MIP commuting is actually contained in the complement of RE, the class co-RE. By the way, I just want to remark that it's kind of neat how there's like this, there's a co on both sides, even though they stand for totally different things. This side is commuting, that one's complement. But okay, so it's kind of fun. But okay, so that's the situation with upper bounds. And then you might ask, well, do we know whether these two notions of entanglement are different? Well, we don't. There's actually a conjecture in math called the Kahn embedding conjecture that says that they are equivalent. So if this conjecture is true, then one consequence is that MIP star would be equal to MIP co, and then the upper bound would be the intersection of these two classes. And the intersection of them is just the set of all decidable languages, R. And so the way you can think about that is that they're equal, the two curves end up converging to the same point, and then the algorithm that decides whether your MIP star protocol has a good strategy or not is it sort of simultaneously iterates over both of these things. It looks for upper bounds, it looks for lower bounds. Eventually, one of these curves will like tell you that either there's no good strategy or there's a good enough strategy. And so this algorithm will always halt. So okay, so that's true if the Kahn's embedding conjecture is true, but otherwise we don't know. So I think the natural question is, can we go further, and then can we get like stronger lower bounds, like non-deterministic towers of exponentials, and could we even try to put like not undecidable problems into MIP star, or even say MIP star is equal to the upper bound of RE. So if we could do that, that would refute this Kahn embedding conjecture. So and then that would be very interesting for a number of reasons. So yeah, I guess that's all I have to say. So thanks for listening. All right. So so you mean like in the protocol, right? Yeah. So the provers have to distribute the entanglement beforehand because they can't communicate during the protocol. That's right.
This last picture that you showed, you got sort of like the limit of the power of exponentials. Typically, sometimes the REs are actually like a receiver.
Yeah. So so not RE in particular. Well, so this paper has some results in this direction. So what they showed is that so if you have a general compression theorem, so like if you have a theorem that takes any MIP star protocol and compresses the question and answer length, then they showed that you could like recursively apply it to itself, and then you wouldn't necessarily get RE, but you get some undecidable problem contained in MIP star. But I don't know, I kind of feel like similar techniques, if this works out, this should maybe be able to get you RE as well. Yeah. Yeah, so okay, let me tell you what we don't know how to do it, well, what's not obvious how to do at the moment. So if you compose it with itself, well, you have to do it like this. You have to first do question reduction, and then answer reduction, and then question reduction again. Like, I think just like doing question reduction twice in a row well, maybe you could do that, but then I think that would, like maybe answer reduction would not work, because, right, because like if you try to do answer reduction on top of something that has answers that are too big, then the questions like blow up too much. So this is the only order that works, is you do question reduction first, then answer reduction, and then question reduction. And then the problem is that when you did this like PCP composition thing, you introduce a bunch of new questions that come from testing the PCP. And so then you have to show that the distribution of those questions is also sampleable from entanglement in the way that we wanted. And that's, well, that involves like delving into the internals of the PCP, and it's kind of technically involved. I don't see like a fundamental barrier to making it work, for sure. So I think it's possible, but yeah. I think it's believed to be distinct. I don't know if it's known to be exact. Yeah. Yeah. Very good question. So actually, we don't know that. We don't even know that NEXP or co-NEXP are contained in MIP co. Like the best lower bounds on MIP co are probably, I think, NP. Because the reason is that like a lot of these soundness proofs involves, there's steps where you assume that the matrices that are describing the measurements are finite dimensional. Like sometimes they even do things like you have a convex program and you plug in the measurements as like variables in the convex program, and all of that is like harder to do with the infinite dimensional case. So I think that's an interesting problem. There is some work by I think Matt Kudron and William Slofstra on lower bounds. I think they have lower bounds for MIP co, but those are in like the small gap regime. So they can show that, say, NEXP is an MIP co, but the gap will be inverse exponential, I think. Uh-huh. No, they're independent of the input. Yeah, yeah. Um, That's not necessarily the case. They're allowed to depend on the input, but in our protocol, they're independent. They're just copies of the EPR state. Potentially, yeah. I don't see a reason to rule it out. I will say that the measurements are very dependent on the input here. Like, that's like where all the input dependence is going. Yeah, like the protocols I talked about based on like the history states. Like in those cases, the states did depend on the input because they were history states of some computation that you have to prove properties of. But, yeah. So it's certainly possible. Sure.
Can you give me more intuition about how this works? How do you make it completely still?
Okay.
What is the strategy?
Well, maybe I'll. Is it okay if I use the? Oh, maybe I can do it over here. So okay, I can tell you the trickiest thing to. The thing that surprises the most is okay. So I can talk about how it works for magic square. Like how do you make this work for magic square? So the standard formulation of magic square, right? That you often hear is that Alice gets a row and Bob gets a column, and you cross-check them on the common cell. And this is not complete for oracularization because, like in the oracularized version, Alice would get both the row and the column, Bob would get just the column, and then Alice would have to come up with Bob's answer not just for these cells, but also for these cells, right? And Alice cannot do that because this doesn't commute with that. So you have to work with this this other version of magic square where Alice gets either a row or a column, and Bob gets a cell. And then this works out because in the oracularized version, Alice will get a row or a column and the index of a cell on that row or column. And Bob will just get either a row or column or a cell. And now what they have to do is, now their measurements commute with each other, right? Because what Bob is asked to do is always a subset of what Alice is doing. And Alice is only ever measuring a single row or a single column. So that's sort of the flavor of how these things work.
Actually, an extra one. It's just one to prove
Yeah. So well, that's right. Yeah.
It's not an addition.
That's right. It's an additional role that one of the provers could play, that one of Alice or